All right, guys, this is a quick tutorial on how to use the calorimetry equation. And this will hopefully set us up to do the calorimetry activity sometime next week. Okay, so we're going to do a quick review of what energy is, and then I'm going to show you how to actually use the equation to help us with calorimetry problems. Okay, so hopefully this will make a lot more sense. I know the reading in the video from the other day were a little bit dense, so we're going to see if we can break it down just a little bit more simply for you guys and go from there. So if you remember initially, we talked about how the total energy of a system is equal to the change in the heat plus the work, right? Those are the two things we have to pay attention to. The good news with chemical equations is that almost always we are in what's called an open system. In other words, open to the environment. And so the work is almost always negligible compared to the heat change. So we don't really need to factor in the work unless we're talking about like a closed system, like in a vacuum or something like that, right? So most of the chemical reactions we're going to talk about, we're just going to talk about Q. So if we want to know how much energy change there is in a reaction, we really just need to know how to calculate Q. So what we're going to be learning in the next probably 2 weeks is like 5 or 6 different ways to calculate a Q value. Calorimetry is one of those ways. And so that's what we're going to do today. So Q is heat, okay? And then the equation we're going to work with today is Q equals mc delta T, right? So Q being heat, okay? And if you remember units that we can use, heat's a form of energy. So we're typically in joules, right? J for heat. We could be in calories, and we'll talk a little bit more about calories later in the week. Calorie is another unit of energy for that. There's a conversion between those two, but joules is going to be the unit we're going to be primarily in. M is mass, okay? C is specific heat capacity. Okay, and T is change in temperature, right? Delta T. It's always going to be T final minus T initial, right? Because that'll help us get the sign right. Because if you remember, the sign is crucial here. Q can be negative, right? Therefore, the change in temperature could also be negative if this is cooling down, right? So what is specific heat capacity? That is, right, very simply, a substance's ability to hold heat, right? So its official definition, which I showed you guys the other day, the official definition is the amount of energy required to raise 1 gram of something 1 degree Celsius, right? So that's the very specific definition of it. That's why it's called specific heat capacity. But in just general terms, it's how much energy a substance can take on without changing its temperature, right? So how good of a job does it do like resisting changes in heat? So if you think about water, for example, water has an incredibly high capacity for heat because it takes a lot of energy to change the temperature of water. It takes a long time to boil a pot of water. It takes a long time for that pot of water to cool off. You look at something like metals, right? They have an incredibly low capacity for heat because they don't hold heat very well at all. They get hot really fast, right? But they lose that heat really fast. They cool off really fast. So they don't retain heat. So they have a very low capacity for heat. Specific heat capacity is a physical property that is unique to every substance. It's just like a boiling point or a melting point. You could look up the heat capacity for a substance just because it's a known fixed value for a substance, okay? So that's good. So when we do this worksheet here in a second, you guys are going to work on some of it on your own. We're going to do a couple together. You can actually, either Google or use your textbook. There's a table in your textbook, the heat capacity for these things when you're doing the problems, okay? So this is a way that we can use to calculate heat. The sign is going to be important. Q can be negative. Well, when is Q negative? When the system loses heat. That should also mean that delta T is negative because if something loses heat, it loses temperature, therefore it cools off. Okay? So let's see if we can apply this to one of the problems. So this worksheet's posted as well on PowerSchool. Like I said, we're going to do a couple together, and then you guys can work on the rest on your own. So look at the first problem here. How much energy is required to increase the temperature of 150 grams of water from 20 degrees Celsius to 90 degrees Celsius? Right? So let's list what we have. We have a mass, which is 150 grams, right? We have a delta T, which is T final minus T initial. So it ended at 90 and it started at 20. So delta T is going to be 70 degrees, positive, right? Because it heated up. How about Q? So it's asking for how much energy. So that's going to be our question mark. That's going to be our X value. So the only other variable we need to figure out is the C, the heat capacity. Again, we know that it's water, so we can look this up. I'm just going to tell you it here. This is a number that you're going to get very familiar with, but this is the specific heat capacity for water. It is 4.18 joules per gram degree Celsius. The unit is key here. Okay, and it's kind of a complicated unit, so pay attention to that, right? It's energy per gram degree Celsius. So it's usually in joules per gram degree Celsius. If you Google this, you may also see it in calories and or kilojoules, right? Those are okay. You just have to pay attention that you're in those units. You might also see it in per Kelvin, not Celsius. That's okay. Because it's a delta T, it's not going to matter if it's Celsius or Kelvin. You don't have to do any conversions there because 1 degree Celsius is 1 Kelvin. So it works out. Okay. Okay. So now we're going to plug it in. We're looking for Q. We're going to do 150 grams. Keep the units so you can make sure everything checks out. 4.18 joules per gram degree Celsius. Delta T is 70 degrees Celsius. So our Q value is going to be, if we actually multiply this out, 1.8 times 70, okay, and look at this, it's going to be a big number, right? Times 70, here we go. So we're going to get 43,890, and we want to know what unit we're doing. So cross off, grams cancels, Celsius cancels, we're left with just joules, but that's good because we solved for energy or heat. So I'm going to say joules. You could put that in kilojoules if you want to. We should round to proper significant figures here. In theory, according to the temperature, we should probably give 1, but I think 2 is probably more reasonable given the mass. So if we do 2 here, that's going to be 44,000 joules or 44 kilojoules. Question is it positive or negative? Okay. How much energy is required to increase the temperature? Okay. So heat is added to the system. So this is going to stay a positive value. Right. So we're going to circle that. This should make sense because our delta T was positive. Right. The delta T is positive, then the overall Q will be positive. That should just make sense from a logic perspective. If heat is added, temperature would go up. Right? But let's think about it from a math perspective too. If we go to our equation here, can mass ever be negative? Right? You should be saying no. Can heat capacity ever be negative? Right? Well, you may not know the answer to that, and that's okay, but let's prove it. Right? So mass can't be negative. Can Q be negative? You should be saying yes. Well, when is Q negative? Q is negative when temperature goes down. In other words, when delta T is negative, right? So when Q is negative, delta T is also negative. So those should offset, which means heat capacity can never be a negative value, okay? Heat capacity can never be a negative value. It should also just kind of make sense that you can't have like a negative capacity for something. Doesn't really make sense. Like think of like your water bottle or something, right? It can't have a negative capacity for water, right? Okay, let's try the next one. And then you guys can finish the rest on your own. The next one. What is the mass of an iron skillet if its temperature increases 250 degrees Celsius when 1,500 joules of energy is added to it? Okay. So we're going to still use the same equation, right? Still use the same equation. And write down what we have. This time, they're looking for mass. That's our question mark. Delta T, it says the temperature increases to 250. Okay? Or, sorry, increases 250 degrees Celsius. So we're only given one temperature. But if you read the language of the problem carefully, it tells you if the temperature increases 250 degrees. So it doesn't give you the final or the initial temperature. It's actually giving you the delta T, which is 250 degrees Celsius. It says when 15,000 joules of energy is added to it. So Q is 15,000 joules. Now, is it positive or negative? What do you think? Right? Temperature increased, right? So it should be positive, but you can also look at the language. 15,000 joules of energy is added. So heat was added to the system. Q should be positive. Delta T should be positive. So now we need to know the C value. So we're going to go to our trusty resource Google, and we're going to look up the heat capacity of iron because it tells you it's an iron skillet. And if you do that, you'll see that it is 0.444 joules per gram degree Celsius. Note that it is almost 10 times less than that of water, which should make sense because water's heat capacity is quite high, relatively speaking, and iron's is quite low, okay? This is why we use metal in frying pans, because we want the pan to get hot really quickly, but we want it to lose the heat really quickly and go into the food, right? And so that's why metal works really well for that. Typically, the handle of the frying pan is not metal. Some of the old school ones are, but you can't hold the metal directly. Most of the modern pans have some kind of silicone or some kind of handle because that has a different capacity for heat, has a much higher capacity for heat, and it won't burn your hand when you pick up the pan. Okay, so let's plug it in. This time we have Q, right? It's 15,000 joules equals M, right? We don't know the mass, that's what we're solving for, times our heat capacity. Keep the units so you can double check your work. And our delta T is 250 degrees Celsius. So now we have to isolate M. So I'm going to take 15,000, right? It's just algebra at this point. We're going to divide by 0.444. We're going to divide by 250. And that's going to give us mass of 135 grams. And if we double check our units, joules crosses out, Celsius crosses out, and we are in fact just left with grams. We should probably, if we're being careful here, round this to 2 sig figs. So I would say official answer is probably 140 grams, if we're being careful with that, okay? So think about that for a second. It seems like a lot, right? But there was a lot of energy, right, and a big temperature change, okay? If we added that same amount of heat to water, we would only see, a very, very, very minor temperature change, right? Basically a tenth of that. So it would only change like 25 degrees instead of 250 degrees, okay? So the heat capacity is very, very, very important. Obviously the mass is positive because mass cannot be negative, okay? So what you guys are gonna do is try to do numbers 3, 4, and 5 here together, okay? You can work in small groups or on your own, however you wanna do it, okay? And try to see how many answers you can get. I will post the answer key to the others a little bit later, so you can check your work later on. The 5th one is a little bit tricky because it's giving you a little bit more of a complicated scenario, but I think you can pull it off, all right? And we'll regroup after the weekend, okay?